Hello, everyone. Give me 1 minute as I figure out how this microphone and how I should be placed so that you can all hear me. It's a pleasure to be here. It's a pleasure to have so many people. I'll talk a little bit about a work that I'm doing with a lot of people, and we have quite a sizable grant, the Encore project grant, that is sponsoring us from EPSRC. This is work mostly done at the University of Manchester, but I will mention some collaborators from other people. So let's just go into it. But maybe some of you need some background on neural network verification. So I'm a machine learning person. I am fairly new to the formal methods game. So when I first landed on neural network verification, I tried to get what is the mainstream. So when people search on Google Scholar neural network verification, what would they land onto? What is the problem setting? So the problem setting tends to be like this. There is some neural network specification, some safety property, and then you want to write a verification algorithm that is able to tell you yes or no whether the safety property holds. And there's competitions already about this, but the real crux here, and the thing that we'll be talking in this talk, is how do you specify the neural network? So usually it's some form of exchange format like ONNX that really matches what the data scientists work on, so some Python stuff, PyTorch, the TensorFlow, something like that. And then safety properties, the mainstream thing tends to be some form of robustness. So precondition, neural network, postcondition, small input set, the output should not change. But I will argue in this talk, if my microphone still works, that this is not very good. And you'll figure out why. So the first of all is this machine learning mindset. Of course, we want to do a tool that, like the previous speaker said, the users want to use. But the machine learning mindset is a little bit too abstract. So the machine learning people and data scientists tend to think in a sort of idealized world where everything is in infinite precision, everything is a real number, the neural network is a function defined in some sort of high-level mathematical domain, and they're happy with that. They can define gradient descent, do all the training and tricks. But the problem is, if we are in a safety-critical system and we want to do verification because we want a guarantee that the thing is not going to break and create damage to someone, this high-level mathematical world is not enough. Because in practice, I mean, we are computer scientists and we know numerical representation computers are finite. So nothing is a real number. We have integers or maybe floating points, and then there's all sort of other non-idealities happening in the computer, parallel execution, approximations, all sort of things. And then the implicit assumption for data scientists is that it's just a tiny little approximation and it's fine, right? But is it fine? And then, of course, the problem is not only is there's the machine arithmetic, but also this machine learning pipeline is built over several layers of software libraries. And software libraries can have all the problems that software has. The fact that it's doing machine learning doesn't matter. If there's a buffer overflow, there's a buffer overflow, right? And all of this can introduce a vulnerability. And I would just to mention, the classic data science workflow uses a lot of open source libraries. So who knows what's going on in them? So not only that, but we need to talk about floating point because the majority of neural networks and the majority of machine learning is built on 32-bit floating point. Of course, there's quantized neural network that work in integer. There is smaller than 32-bit floating point. The computer engineer have been trying to optimize things. But there's a lot of floating point going on, and floating point we know is evil. But it's not just evil, in general, but there's practical problems that happen by using floating point. So there's a few papers, I keep collecting them, from the machine learning community. So these are not formal methods people. They try to figure out what happens when we trust this long pipeline of layers of software libraries that we don't know really how they work, all sorts of abstractions, and everything works in floating point. And basically they are discovering that we don't even have the classic engineering safeguards of if I develop a system and then I deploy it, once I deploy it, the system is doing what I think it's gonna do. And so they say, okay, a data scientist is developing, let's say, an image classification neural network on that development platform, and then they are deploying, let's say, on a mobile phone. And depending on the mobile phone, depending on not just the camera, but the algorithm that does the image compression, depending on which sort of convolution algorithm they use inside the neural network, depending on the order of the floating point operations, and depending on the whole pipeline until the user gets the image classification, oh yes, this image contains a dog or not. You can, depending on all of that, you can get up to 6% accuracy fluctuations. And for a machine learning person like me, I mean, you can publish a paper if you get 1% improvement on accuracy on some benchmark. So the idea that the same neural network that may be state of the art, I deploy it on a different phone, and it's just awful, and there's no control because it really depends on tiny details that accumulate over the whole processing. It's not nice. And this, unfortunately, carries on to the formal methods community. So there's quite an active, small sub-community that does neural network verification. And they try to do neural network verification, again, on this abstract, infinite precision world. But then their tools are not really sound and use floating point. So they have these strange ambiguities where the specification is in floating point, but we pretend it's real numbers. And the tool is actually implemented in floating point is not really sound, but we pretend it's working in infinite precision. And as a result, most existing neural network verifiers, sometimes they give you a false result. And the false result means sometimes they find a counterexample, but once you try to reproduce it on a specific architecture, on a specific library, on a specific setting, the counterexample may just not exist anymore, just disappears, which is a problem. It's a problem because, like, in the end, in a safety critical system, you want to know that your system is going to be safe, it's going to never exhibit a certain behavior, but now you cannot really trust your pipeline, right? Because it really depends on which library you're using, which device you're running it on, all sorts of low-level considerations, and your beautiful infinite precision real-world abstraction is not helpful anymore. So we need to do something else, which we call bit-precise neural network verification, where we need to give to the verification algorithm more information about what's going on. And this information is, of course, numerical representations, floating points, integers, something that tells exactly how I'm manipulating numbers, but also software libraries. So in this way, we know exactly the order of the floating point operations, so we don't have problem with associativity and commutativity. And we hope to get a sound proof. Of course, up to the hardware misbehaving, right? We are not going down to hardware level. Okay, so how do we do this? By adding all this stuff is beginning to sound a lot like software verification, right? The fact that this is a neural network or a machine learning component doesn't matter anymore. Just give me the code and I will verify the code. And of course, like, there's no point of developing another software verifier. You know, there's decades of research. Let's see how existing software verifiers do on neural network code. And surprisingly, this has never been tried before. And so the first thing we did is build a benchmark. So we wanted this benchmark. Well, we had several requirements. First of all, we wanted really to talk to the software verification community, which very much likes C code. And then we wanted to have some realistic use cases, so we ended up doing microcontroller software. And we wanted some sort of check that the verifiers, the software verifiers, are telling us the truth, right? Because the problem we have with existing neural network verifiers is that sometimes they don't tell us the truth because they are using this real-world abstraction. Are the software verifiers telling us the truth? So we want to build a benchmark that has a known ground truth. If you want more details, there is paper on archive. I'll tell you more about this. I don't want to get too much in the detail of how we build the benchmark, but at least give you an idea of what it looks like, right? So we built about 600 different instances of this benchmark. It covers from very simple components of a neural network, which is just maybe just a mathematical function like an exponential, an activation function, to small and large quote unquote neural networks. So the largest neural network has something like 1,000 neurons, which from machine learning standards is just tiny, but for verification standard, it does get sizable. And this is all C code. So you can imagine a piece of C code. There will be some very large arrays containing the neural network parameters, and then there is some matrix multiplication, some nested loops with matrix multiplication, and we wrote a lot of reachability properties. So this is not memory safety. These are the nasty robustness properties that says for a small input set, the neural network will never say this, or will always say that the image contains a cat, or something like that. And we spent a lot of effort checking a priori what will be the result of the verification query, and we made it sure that we have a balance set that's like about half of the benchmark is safe instances, and about half of the benchmark contains a counterexample. And then we tried software verifiers. So this is a bit of a story. Started last summer. And well, at first we did it in-house, right? So we downloaded a lot of software verifier. Our group has a history of working with software verifiers. And we just ran them on the benchmark. And we started getting very strange results. So if you see this graph, right, the yellow part is fine. So you have a lot of unknown results, but that's expected, right? Sometimes the verification instance is just too difficult, and the verifier will crunch for minutes, maybe hours, and then give up and have a timeout. What is very troubling is that software verifier are supposed to actually work on the bit-precise behavior of the code, and they were giving us a lot of incorrect results. So these are state-of-the-art software verifiers. We checked out benchmarks so many times, and yet, some of them you can see hundreds of wrong results. So we tried to figure out why this was happening, and we got some ideas. Okay, so first of all, we figured out a lot of these state-of-the-art software verifiers do not contain models of the mathematical library. So as soon as the neural network contains some activation functions, let's say like a sigmoid, that depends on exponential, there will be a call to math.h. The verifier does not have a model of what this does, so it will just return strange counterexamples that make no sense. The unknown results is fine, but okay, this cannot justify the number of incorrect results we were getting. And so this was our feeling last summer. It's like, okay, we really, really would like to have bit-precise verifiers, but everything seems broken, which, I mean, it's okay for us, we are researchers. Oh, we have a question. Yes, please.
Hey, when you say that the verifier is giving the incorrect result, yes, is that saying that it's okay, but it's not okay, or it's saying that it's not okay, but it actually is okay? Like, is it false positive or false negative?
Yeah, that's a brilliant question. We would have liked it to be either, but unfortunately it was both. So sometimes we're lying with false counterexamples, and sometimes they were just telling us it's safe when we knew there was a counterexample. Yeah. Oh, we have another question. That's exciting.
Claim there isn't a spec for what exponential does in C.
Yes, that's the other
So
question.
how do you know your results are right or wrong when there really isn't a spec for this?
Yeah, so that's one of the problems, specification problems. So first of all, I want to say sometimes we got incorrect result also when there were no mathematical functions. So it was just multiplication, additions, some array operations, some ifs. Regarding the spec, I agree with you, and this is like the classic questions we get. IEEE standard mandates the behavior of just some mathematical functions, like fuse, multiply, add, or square root, like very few. And for most of them, it's up to the hardware, it's up to the compiler to define. Like my problem is that from the machine learning perspective, so I bring back the user case, right? From the machine learning perspective, the data scientist assumes that this is gonna work, right? Up to fairly precise approximation. So that's the first problem. So from the user perspective, they will write a code and will assume that this is gonna work, so we need to have a way to verify it. The second thing is, we actually tried also to include in our benchmark some operational models that were written in C. So some piece of C that actually computes exponential and it's bit precise. We were still getting correct results. So, of course, the details, it's way more complicated. So we can take it offline. I mean, we are also currently working on turning this into a very long journal paper because of all these details on specification and mathematical operations. I hope that was enough of a teaser, and then we can have a lengthy discussion afterwards. But yeah, so apart from this specification issue with math, our first worry is that we were doing something wrong, right? And so we decided, okay, let's try and submit this benchmark to software verification competition for various reasons. Most important is because there will be an independent team that runs the experiment from us, so it's not going to be our fault anymore. So there's been some discussion, including some of these questions. Some authors of some tools started trying to get a discussion that the way we were dealing with floating points in neural network was not conventional. And therefore, our benchmark should have been kept in a separate category. And that was, for the people who knows the SPCOM community, sometimes there's some fiery discussions. But in the end, the benchmark was approved, so it's there. All future edition of SPCOM will use it. So from now on, when you download a software verifier that competes in SPCOM, they will have been tested on neural network code as well. And of course, I mean, at Manchester, we also developed a software verifier, and our software verifier was broken too, so we needed to put the work to fix it. So I can show you the sort of before and after of the competition. So again, at the top is these results that we ran in August. And then after the competition, a lot of the tool authors rushed to fix things. And now it looks much different, right? So you can see that the number of incorrect results have disappeared. A lot more unknowns, of course, but also fewer correct results. Because sometimes also these correct results were not really correct results, were guesses. There were bugs, so in the end the verifier was guessing at random, and sometimes by guessing at random you get it lucky, right? So now you have this, and of course I can also show you the full SPComp results. So for the people who are authors of these tools, I'm very sorry, but these are official results. And of course, these are not the result of the all SPComp, just our 600 neural network benchmarks. So you'll see a lot of tools. Of course, we are very happy about our tool from the University of Manchester that gets no incorrect results and a lot of correct results. And you see that there's some big project software verifier from industry, which I guess they have other goals, so they're less keen in soundness and maybe more keen in falsification. But overall, we were very happy about the response of the community because a lot of people jumped in to fix the bugs that our benchmark revealed. And so now we're happy, right? Now we have bit-precise verifiers of neural network, and we are done. Except we aren't really, for various reasons. So the first reason is that, okay, now we have software verifiers that have been patched, but they work on C. This is not really what machine learning developers use, right? Most machine learning developers work in Python, and they work with this high abstraction. So even in some exchange format, like if you say save neural network in Keras or TensorFlow or some of the exchange format like ONNX, it doesn't really specify the order of the floating point operation or also the sort of tiny details that you need to do bit-precise verification. So in the future, we'll probably be looking at some more low-level machine learning compilers like Apache TVM. But then, of course, the other problem is scalability, right? Nobody cares about verifying a neural network with 1,000 neurons, right? It's just tiny. It may still have some applications from some very power-limited applications, but of course, we would like to scale to millions of neurons. But also, and the things that I will present next is like, okay, once you actually have this sort of bit-precise verifier, apart from answering queries with it, which is nice for audit maybe, but is there something more interesting that you can do with it? And one of the things we explored in our group is like, okay, once you have a bit-precise verifier, can you use it for synthesis? So I'll talk a little bit about neural network synthesis. And the use case we worked is for quantized neural networks. This is a bit of a hot topic as computer engineers want to reduce the power consumption of large machine learning models. And they said, well, throw away the floating point worked in integer arithmetic. And of course, quantization is an old technique from signal processing, but applying it to machine learning models is a bit tricky, especially because the errors accumulate over the layers. And if you also want to do training, you need to figure out a way to propagate the gradients backwards, but now the derivative is 0 everywhere, so you need to find some tricks. And there's all sort of very interesting literature from the machine learning world about how to do this. But from the verification side, in the end, you just have some code that works in integer arithmetics and computes a neural network. Now, you might have some specification that tells you, I want the neural network to be safe according to some idea of safety that could be robustness, or in the case of quantization, equivalence to the floating point original neural network that I'm quantizing. And what the literature found, that we also found, is that it really depends on the number of bits of each neuron, how you quantize. It really depends on the tiny details of what you're doing. You may make or break the specification, and it's fairly nonlinear, right? So you can't say, oh, if I use more bits, then it will be more safe. It's just absolutely random, which means that if you want to do synthesis, you need to fundamentally find the right quantization scheme for each neuron in the neural network such that you satisfy your specification. And it's a little bit of trial and error because there's no structure in this sort of matrices. And so what we came up with as a first try is a nice iterative approach. So you just start from some quantization schemes and then you verify. If it is safe, you're happy. If you're not safe, you try again with a different quantization scheme and you keep repeating until you hopefully get a safe quantized neural network. Now, of course, since verification is so non-scalable and slow, we needed to find some tricks to get the first part of this trial and error done as quickly as possible. And so the idea is to mix testing with verification. So over time, If you are unsuccessful, you will build a set of counterexamples that broke your property. And once you try a different quantization scheme, you can at least very quickly check if your new quantization scheme satisfies that set of tests. If it does, then you move on to the slow verification side, and you rinse and repeat. And now, of course, the question is, how many iterations? Because if you need millions of iterations, it will still be unfeasible. But what our student found, and it was very nice, is that you just need a couple of iterations to converge. Of course, you still see some timeouts. So in the verifier column, you see ESBMC. That will be a bit-precise verifier. And then you'll have this NN equiv. That's not a bit-precise verifier. So it's faster, but sometimes lies. Up to you to choose if you want to be slow and precise, or faster and sometimes non-precise. But you can see in the worst case, we needed 13 iterations before we stumbled on a safe quantization schemes. And of course, you can go, this is a small percentage of all the tables that are in our journal paper. So if you're interested, please refer to the paper. So this is the end of my talk. And I hope to have convinced you a little bit that it's interesting to look into bit-precise neural network verifiers, because that's the really only way to have false positive and false negatives, if the user cares about them. And, but it's tricky, and even current verifiers that may promise to be bit-precise, they might not have been tested a lot on neural network code, and so you may uncover a lot of bugs. And of course, once you try to apply it, so not just do verification, but use verification for something else, then scalability hits you very hard, and you probably need some workaround, like we did with this iterative testing and verification method. So hopefully you have more questions, and hopefully they are not difficult questions that we need to take offline.
Thank you. So yes, any difficult questions?
Thank you for that very interesting talk. Right, early on you said that there were specifications that you weren't that happy with, and then later on you found specifications that you were happy with. And now you've got the scale problem. Could your insights help with making testing systems for neural networks?
Definitely. The big problem in neural network verification is to come up with a reasonable specification.
Exact same problem in testing.
Yes.
Right?
Yes.
Spec is the problem.
So, of course, if you care about software and bit precise, you can inherit all the specification that already exists, like buffer overflow and division by zero. Then you have this sort of signal theory inspired or control system inspired properties like robustness, equivalence, of course, if you're doing the transformation, but the real black hole in machine learning specification is, in the end, the user will like to write something like, I am sure that the image classifier can recognize a cat. But, like, how are you going to write that? You can't. And so it's all a game of finding some workarounds, some metamorphic properties, something. So there are papers just about writing the specifications. And then once you have the specification, usually the first thing you do is testing. And only verification in safety critical systems.
Is it they're still doing research about what's good testing for neural networks?
Yes.
Or is that?
I would say it's a bit like with software. The majority is testing, and then there's a smaller community that does verification.
Thanks for the great talk. I had a question about your very beginning. You said that the VNN-com verifiers made a mistake and you weren't able to find a counterexample.
Yes.
Did you ever compare if your integer precise thing actually always fixed the problems you found with the existing non-precise verifiers? So of course it doesn't scale as well, but for the ones you could check.
Yes. So after most software verifiers have been patched for the bugs, I trust them a little bit more. And they can reason about floating point and find some very tricky cases. I also know that there's people that trying to take the unsound proof by a high level, let's say neural network verifier, and then trying to make it sound if they can, right? That's also an active area of research.
Yes, my question is more, when should I use Alpha Beta Crown? When should I use your tool? What do I gain if you saw the verifiers struggle to actually produce anything except yours?
So my point is that, I mean, and maybe I am a bit too strong on this. Like, my point is, like, the only point of using verification is because you really want some guarantee about your result or about the system. Otherwise, you would just test it a lot, because that's faster and easier to do. And so, like, what is really the point in using a verifier that you know can lie to you? Like, you spend a lot of computational effort, and then you have a result that you don't know if it's even true. Like, I don't know. It, like, personally feels a bit, you're breaking the purpose of verification. But maybe I am wrong, and there is a better way.
We can discuss offline.
Yes.
Okay, so thank you very much for that talk, and let's thank Edoardo one more time.